Imagine rolling a ball toward a hill. If you don't give it enough of a push, it climbs part way, stops, and rolls back down. Always. No amount of wishing gets a ball over a hill it doesn't have the energy to climb. This is the most obvious rule in all of physics, the kind of thing you've known since you were a child. And deep inside every atom, that rule is quietly, constantly broken. Particles routinely turn up on the far side of walls they should never be able to cross. They don't smash through them, they don't sneak around the edges, they don't borrow a burst of energy and leap over the top. The wall is real, the energy is genuinely missing, and yet, somehow, the particle is simply there on the other side. This one impossible sounding act lights up every star in the sky and powers the device in your hand. Tonight we find out how. Before we go any deeper, if this is the kind of thing you love thinking about, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Picture a single particle drifting through empty space. It's small beyond imagining, far tinier than an atom, and it's heading towards something that, from its point of view, might as well be a mountain. Up ahead, there's a region it would cost energy to enter. A wall. Not a wall made of brick or stone, but a wall made of energy itself. A place where the rules say you must pay a toll to pass, and the toll is more than this little particle is carrying. It approaches the wall. It slows. And then, by every rule of physics you've ever been taught, it should stop and turn around and come back the way it came, because it simply does not have what it takes to get through. That's the end of the story. That's what has to happen. Except sometimes it isn't what happens at all. Sometimes a detector placed on the far side of that wall, the side the particle could never reach, lights up. The particle is there. It crossed something it had no business crossing. And tonight, we're going to find out exactly how that's possible. Not by hand-waving, not by saying the universe is just weird, but by understanding the precise, careful, almost beautiful mechanism that makes it real. Let's start with the thing that feels obvious, because the whole mystery only becomes a mystery once you appreciate just how certain the ordinary world is that this can't happen. Think about rolling a ball up a hill. You give it a push at the bottom and it rolls upward, slowing as it climbs, because it's trading the energy of its motion for the energy of its height. The faster you push it, the higher it climbs before it runs out. If you push it hard enough, it crests the top and rolls down the other side. If you don't, it climbs part way, stops at the moment all its motion energy has been spent, and then rolls back down toward you. There's a specific dividing line here. There's a certain speed, a certain energy, that the ball needs in order to reach the very top of the hill. Below that energy, it never makes it. Above that energy, it always does. And right at that line, it just barely crawls over. This is something you understand in your bones. You've watched balls roll and stop and come back your entire life. Nobody has ever seen a ball that lacked the energy to climb a hill suddenly appear, calm and intact, sitting on the far slope. The hill stops it. That's what hills do. Physicists have a name for that hill. They call it an energy barrier. And the idea is exactly what it sounds like, just stripped down to its essential form. An energy barrier is a region of space that would cost a particle more energy to occupy than it has available. The hill is a perfect everyday version of this, because climbing the hill means gaining height, and gaining height means storing energy in the form of position, what physicists call potential energy. The higher you go, the more potential energy you hold, and that energy has to come from somewhere. For the rolling ball, it comes from motion. So the top of the hill represents a maximum, a peak amount of potential energy, and to get past it, you need enough motion energy to pay for that peak. If your total energy is less than the height of the peak, there's a stretch of the hill, right near the top, where you would need to have negative motion energy in order to be there. And negative motion energy is nonsense in the ordinary world. Motion energy depends on speed, and speed squared is always positive, so the energy of motion can never drop below zero. That region near the top, the part you can't afford, is what we call classically forbidden. Forbidden not because some authority banned it, but because the arithmetic of energy says a normal object can never be found there. It's a place the bookkeeping won't allow. Now, I want to make sure this notion of a barrier feels real and not just like a math trick, because energy barriers are everywhere once you start looking. When you push two magnets together with their like poles facing, you feel a growing resistance, a wall of force that builds the closer they get. That resistance is an energy barrier. You're paying energy to push into a region the magnets don't want you in. When a chemical reaction needs a spark or a flame to get started, even though the reaction itself releases energy once it's going, that initial nudge is there to push the molecules over an energy barrier, a hump they have to clear before they can tumble down into the lower energy state on the other side. When a charged particle approaches another charge of the same sign, the electrical repulsion between them rises and rises as they close in, forming a steep wall of energy that resists their meeting. In every one of these cases, the picture is the same. There's a hill, there's a peak, and there's a minimum amount of energy you need to get over it. Below that minimum, the classical world is unbending. You stop, you turn back, you do not cross. So let's hold the classical world to its promise and watch what it predicts for our little particle, because the prediction is absolute, and the absoluteness is the point. The particle comes in carrying some amount of energy, all of it in the form of motion. It meets the barrier. As it tries to climb, its motion energy gets converted into the stored energy of being inside the barrier, and it slows down, exactly like the ball on the hill. If its energy is below the top of the barrier, it reaches a point where every last bit of its motion has been spent, and it's still partway up the wall, still inside the forbidden region's outer edge. At that instant, it has zero speed. It can go no further. And because the barrier is still pushing back on it, still sloping upward ahead, it gets shoved back the way it came, gathering speed again as it descends, until it's racing back out into the open space behind it, travelling away from the wall it could not cross. A classical particle facing a barrier taller than its energy reflects, 100% of the time. There is no probability involved, no chance, no maybe. The classical world doesn't deal in maybes here. The reflection is guaranteed as the ball coming back down the hill. If you set this up 1,000 times, 1,000,000 times, 1,000,000,000,000 times, the particle bounces back every single time, and the far side of the barrier remains forever empty. That's the prediction. That's the iron law. And it's wrong. It's wrong not because the math of energy is wrong, but because we made an assumption right at the very beginning, so quietly that we didn't notice we were making it. We assumed the particle is a tiny ball. We assumed it's a little speck sitting at one definite location, travelling with one definite speed, following one definite path through space, the way a marble rolls along a track or a planet sweeps around the sun. That assumption is the thing that fails, and it doesn't fail by a little, it fails completely. A particle, at the smallest scales of nature, is simply not a tiny ball, and almost everything strange about the quantum world flows from taking that fact seriously instead of brushing it aside. Here's what I mean. When you imagine a marble, you picture it as being somewhere. At any given moment it has a home, a point in space you could put your finger on, a here. And it has a velocity, so you could say not only where it is, but where it's going and how fast. Give me those two things, and Newtonian physics will tell you everything the marble will ever do, like winding up a clockwork machine and watching it tick out its future. The marble's whole life is a single thread, one unbroken line traced through space, every point on that line a place the marble truly was. This is how the everyday world behaves, and it's so reliable that we built bridges and rockets and entire civilizations on it. But it is not how the smallest pieces of matter behave, and the failure isn't a small correction or a rounding error, it's a different kind of thing entirely. A quantum particle does not have a single definite position waiting to be discovered. Before you look, before you measure, it is not sitting at one spot keeping its location a secret from you. The situation is stranger and deeper than secrecy. The particle is described instead by something spread out across space, something that exists in many places at once, something that assigns to every point in space a kind of presence, a measure of how much the particle is there. Physicists call this object the wave function, and I want to slow down here because the wave function is the single most important idea in this entire story, the key that unlocks everything that follows. If you understand the wave function, even roughly, even just its flavor, then the mystery of crossing the impossible wall stops being magic and starts being almost inevitable. So what is this thing? The wave function is a description of the particle that is spread out over a region rather than pinned to a point. Think of it less like a pebble and more like a ripple or a haze or a cloud that's denser in some places and thinner in others. Where the wave function is large, the particle is, in a sense, strongly present. Where the wave function is small, the particle is only faintly present. And where the wave function is zero, the particle is absent. The particle isn't a dot hiding inside this cloud, waiting for us to find which point it's really at. The cloud is the particle's reality. The spread outness is not our ignorance about where the dot is. The spread outness is the actual nature of the thing. There is no dot. Now this raises an obvious and fair objection, and it's worth confronting head-on. You might say, but whenever anyone has ever measured a particle, they've found it at a definite place. A detector clicks at one spot, not smeared across a region. A speck shows up on a screen at a particular point. So how can the particle be a spread-out cloud if we always catch it somewhere specific? And this is exactly the right question, because it points at the deep and genuinely surprising heart of the matter. The wave function does not tell you where the particle is. It tells you the probability of where the particle will be found if you look. The size of the wave function at each point, when you handle it the right way, gives you the odds, the likelihood, the chance of detecting the particle there rather than somewhere else. Where the wave function is large, you're very likely to find the particle. Where it's small, you're unlikely to find it. Where it's zero, you'll never find it. And the act of looking, the act of measuring, is itself part of the story. Because before you measure, there's no definite location at all, only this landscape of possibilities. And the measurement is the moment a single, definite outcome crystallizes out of the spread. Let that sink in, because it overturns the marble completely. The marble was at one place and we just had to find out which. The quantum particle is not at one place. It carries a distribution of possibilities, and only when reality is forced to give an answer, through a measurement, through an interaction, does one of those possibilities become the answer. The wave function is the menu of what could happen, weighted by how likely each option is. It is the realest thing about the particle, more real than any single position, because the position is only ever one sample drawn from the wave function's odds. If this sounds unsettling, it should, and you're in excellent company. Some of the greatest minds in the history of science found it deeply uncomfortable. But discomfort isn't evidence against an idea, and the evidence for the wave function is overwhelming, woven into every successful prediction of quantum physics, confirmed in countless experiments across more than a century. The world really does work this way at the smallest scales. The spread-out wave function, the probabilities, the absence of a definite path. These are not philosophical preferences. They are what nature does, measured again and again with a precision almost beyond belief. And here is where you can start to feel the wall begin to crumble, even though we haven't yet reached the heart of the explanation. Go back to the marble for a moment. The marble had one path, one thread through space, and that thread was blocked by the hill, full stop. Because every point on the thread had to be a place the marble could really be, and the forbidden region was off limits, so no thread could pass through it. The marble's whole problem was that it needed a continuous line over the top, and it couldn't afford the top, so no line existed. But the quantum particle doesn't have a thread. It doesn't travel along a single line of definite positions. It's a wave function, a spread-out distribution of where it might be found. And once you stop asking, what path does the particle take over the hill, and start asking, what does the particle's wave function look like in the neighborhood of this barrier, You've stopped asking the question that has no good answer and started asking the question that does. The marbles question was a trap because it assumed a thing, the path, the thread, the definite line of being, that the particle simply does not possess. This is the reframing that changes everything, and it's worth saying as plainly as possible. The reason a classical object can't cross a barrier it lacks the energy to climb is that a classical object's existence is a continuous trajectory, an unbroken chain of real positions. And that chain has to include the forbidden region in order to reach the far side. And it can't, so it doesn't. The whole argument depends on the particle being a thing that occupies a definite point at every instant and traces a connected line through space. Take that picture away, replace the line with a spread-out wave function, and the airtight classical argument loses the very floor it was standing on. We are no longer talking about a little ball that must be somewhere along a path. We are talking about a distribution of presence that exists across a region, and the question of what that distribution does when it encounters a barrier is a completely different question with a completely different answer. I want to be careful here, because it would be easy to overshoot and say something false. I'm not telling you that the wave function lets the particle do absolutely anything, or that quantum physics means rules don't apply, or that the barrier is an illusion. None of that is true, and as we go further, you'll see how tightly controlled this whole phenomenon actually is, how the barrier matters enormously, how the odds are pinned down by precise and unforgiving rules. The barrier is real. The energy the particle lacks is real. What's not real is the assumption that the particle is a point on a path, and once that single assumption falls, the door opens, not to chaos, but to a new and exact kind of bookkeeping, one built on amplitudes and probabilities instead of trajectories and certainties. Let me try to make the wave function picture even more concrete, because abstraction can slip away from you if it's not anchored. Imagine the particle, before it ever reaches the barrier, drifting through open space. Its wave function in that open region looks like a wave, an undulating pattern that rises and falls, marching along through space. This wavy character is not decoration, it's tied directly to the particle's motion and energy. A more energetic, faster-moving particle has a wave function that wiggles more tightly, with crests packed close together. A slower, gentler particle has a wave function with longer, lazier undulations. The wave nature is bound up with how the particle moves, which is why we sometimes speak of the particle's wave aspect and its particle aspect as two faces of one underlying reality. Out in the open, away from any barrier, this wave just rolls along, carrying the particle's presence forward, spread out but travelling, every part of it allowed, every region one the particle can afford to occupy. There's nothing forbidden out here. The wave is at home. Before we watch the wave meet the wall, there's a quiet rule we have to put in place, because without it, none of what follows would be forced to happen. The wave function is smooth, it is continuous, it does not jump. Wherever you look along it, the wave joins up with itself. No breaks, no sudden cliffs, no places where it leaps from one height to another with nothing in between. This sounds like a small technical point, but it is the hinge the entire phenomenon swings on, so I want to make it feel as real as the wave itself. A wave function that suddenly snapped from some height to zero, or from one value to a completely different value with no connection between them, would correspond to physical nonsense, to a particle whose behaviour couldn't be described by the rules that govern every quantum state. Nature does not allow it. The wave has to flow, joined to itself at every point, like a rope laid across the ground rather than a row of disconnected pieces. Now feel what that rule demands at the edge of the barrier. Just outside the wall, the wave function has some height, some real value, the tail end of the rolling wave that carried the particle in. The continuity rule says the wave cannot simply cease to exist the instant it touches the forbidden region. It cannot hit the surface of the wall and drop to nothing, because that would be exactly the kind of sudden cliff the rule forbids. Whatever value the wave has at the boundary on the outside, it must have that same value at the boundary on the inside, joined smoothly across the edge. The wave is obligated to continue into the barrier, because the alternative, stopping dead at the surface, would tear the wave function apart at the seam. So the leak we're about to follow is not an optional quirk, it's compelled. The moment you accept that the particle is a smooth, continuous wave, you have already accepted that the wave must extend past the wall, because a continuous thing cannot vanish at a line. The only freedom the barrier has is to decide how the wave behaves once it's inside, not whether it enters. And we've seen what it does once inside. It decays. There's a second feature worth pulling into the light here, because it sharpens the whole probability picture, and it's easy to miss. When the wave reaches the wall, not all of it goes in. Most of it, in fact, usually bounces straight back. Part of the wave function reflects off the barrier and travels back the way it came, exactly as a classical particle would, while only a portion continues into the forbidden region to begin its decay. So a tunneling situation is not a wave that obediently marches through the wall. It's a wave that splits, with the larger share reflecting backward and a smaller share pressing into the barrier to leak across. This matters because it means the probability of crossing is genuinely the minority outcome in most realistic cases. Send a single particle at the wall and it will very likely bounce back, its reflected wave dominating. Only occasionally does the faint transmitted thread win out and the particle turn up on the far side. The reflection and the transmission are two parts of one continuous, smooth wave, the book's always balancing, every bit of the wave accounted for, some sent back, some leaked through. The barrier doesn't have to choose between reflecting the particle and transmitting it. The wave does both at once, in proportions the barrier sets, and only when the particle is finally detected does one outcome become the answer. Then it arrives at the wall, and the question that decides everything, the question this whole story turns on, is simple to state. What does the wave function do when it reaches a region the particle classically cannot afford? Does it stop dead at the surface, snapping abruptly to nothing, refusing to enter the forbidden zone the way a classical ball refuses? Or does it do something else, something that the marble could never do, something that follows from the wave function being a smooth, continuous, wave-like thing, rather than a hard little point? Hold on to that question, because the answer is the engine that drives the entire phenomenon, and it's the most important thing we'll uncover. For now, just feel the shape of where we've arrived. We started with an iron law. A particle without enough energy must bounce back, always, with no exceptions. We found that the iron law rests on a single hidden assumption, that the particle is a tiny ball tracing a definite path. And we discovered that this assumption is false, replaced in reality by a spread-out wave function whose meaning is probability, whose nature is to be many places at once until a measurement forces a single answer. Notice what we have and haven't done. We have not yet explained how the particle ends up on the far side. We've done something more basic and more important. We've cleared away the reason you might have thought it impossible in the first place. The impossibility was never a feature of the particle. It was a feature of our mental model, the marble model, smuggled in from the world of everyday objects where it works beautifully, and applied to a realm where it quietly breaks down. The barrier didn't lose its power. Our intuition lost its grip. And that's the right place to be standing, because from here, the rest of the explanation isn't a leap of faith. It's a careful, almost gentle following of what a wave function naturally does, with no rule-breaking required, and nothing borrowed and nothing smashed. There's one more thing I want to leave you with before we go inside the barrier itself, because it sets the tone for everything ahead. In the world of marbles and hills, a barrier is a wall, an absolute, a hard yes or no. You have enough energy or you don't. You cross or you reflect. There's a sharp line, and which side of it you're on determines your fate with total certainty. But the quantum world doesn't speak in absolutes like that. It speaks in amplitudes and probabilities. It doesn't say, you cannot be there. It says, you are unlikely to be found there. And unlikely is a very different word from impossible. Unlikely still leaves room. Unlikely is a number greater than zero, however small, and a probability that's small but not zero. repeated across the enormous numbers of particles that nature deals with every instant, in every atom, in every star, becomes not a curiosity, but a certainty of its own kind. Things that almost never happen to a single particle happen constantly when there are unimaginably many particles, each rolling its own dice, moment after moment, for billions of years. So the wall, the energy barrier we began with, the hill our little particle could not climb, is about to change its meaning before our eyes. It was a verdict. It's about to become a probability. It was a closed door. It's about to become a door that's almost always shut, but not quite. And that almost is where the entire mystery lives. The classical world handed us a particle that must turn back. The quantum world is going to hand us back a wave function that mostly turns back, and faintly, persistently, with odds we can calculate to as many decimal places as we like, does not. To see how that faint persistence comes about, we have to follow the wave function past the surface of the wall and into the forbidden region itself, into the place the marble could never go, and watch what a wave does there when the rules say it shouldn't be there at all. That's where the real machinery is. That's where a particle learns to be found somewhere it was never supposed to reach. And it does it without breaking a single law, without borrowing a single jewel, without ever once behaving like the tiny ball we so badly wanted it to be. What we'll find inside that wall is not a particle sneaking through a tunnel, despite the name this whole phenomenon eventually earned. There's no little sphere boring a hole and slipping out the other end. What we'll find is something stranger, and once you see it, far more satisfying. A wave that doesn't end where it's told to, a presence that thins but refuses to vanish, an amplitude that bleeds across the forbidden zone and emerges, diminished but alive, into the open space beyond. The particle isn't crossing the barrier the way a person crosses a bridge. The particle is a thing whose very existence is smeared across space, and that smear, that wave function, simply does not respect the hard edge the classical world drew around the forbidden region. The edge is real, the barrier is real, but the wave function leaks. And in that leak, in that quiet refusal of the wave to stop where it's supposed to, lies the answer to how anything at all gets across a wall that should have stopped it cold. We've earned the right to ask the real question now, the one the marble could never have prepared us for. Not, how does a ball get over a hill it can't climb? That question has no answer, because balls don't, and the question is broken. The right question is, when a spread-out wave of probability meets a region of space that classical energy forbids, what shape does that wave take? And does any of it survive to the other side? That question has a precise, calculable, experimentally confirmed answer, and following it will take us into the strangest and most elegant territory in all of physics. The particle approaching the wall is not a pebble at a point. It is a wave of possibility. And what a wave of possibility does at a forbidden boundary is about to dissolve the oldest, most stubborn certainty we carried into this story. The certainty that some walls simply cannot be crossed. We left our particle at the surface of the wall, carrying a wave of possibility instead of a definite position, and we asked the one question that decides everything. When that wave of probability reaches a region the particle classically cannot afford to enter, does it stop dead at the edge? Or does it do something a marble could never do? Now we go inside. We follow the wave function past the boundary, into the forbidden region itself, into the place the classical particle could never be found, and we watch, slowly and carefully, what a wave actually does when it's told it isn't allowed to be somewhere. This is the heart of the whole thing. Everything before was clearing away bad assumptions. Everything after is consequences. Right here, in what follows, is the actual mechanism, the gear that turns, the reason a wall stops being a wall. Start with the open space behind the barrier, before the particle arrives, where the wave function is just rolling along as a wave. Remember its character out there. It oscillates. It rises to a crest, falls to a trough, rises again, marching forward through space with a steady rhythm. That oscillation is the signature of a particle that's free to move, a particle with energy to spare, energy in the form of motion. The wave wiggles because the particle is, in the wave language of quantum physics, doing what a moving particle does. Crest, trough, on, an undulating ribbon of probability sweeping toward the wall. Where the wave is tall, the particle is likely to be found. Where it's near zero between crests, the particle is unlikely to be found right there. But the overall pattern keeps its height as it travels. The crests stay roughly as tall further along as they were further back. The wave doesn't fade as it moves through open space. It just keeps rolling, carrying its full presence forward, because nothing out here is forbidden, and nothing is draining it away. Then it meets the barrier, and the rhythm breaks. Inside the forbidden region, the wave function stops behaving like a rolling wave, and starts behaving like something else entirely. It stops oscillating. The crests and troughs vanish, and in their place, the wave function does the single most important thing in this entire story. It decays. It droops. From the moment it crosses the boundary into the forbidden zone, the wave function begins to shrink, smoothly and steadily, getting smaller and smaller the deeper into the barrier you look. Not wiggling anymore, just diminishing. A curve that starts at some height at the near edge of the wall and slides downward as it pushes into the forbidden region, like a slope descending into a valley, lower and lower with every step inward. Why does it do this? Why oscillate outside and decay inside? The reason is the whole point. Out in the open, the particle had motion energy, and that motion energy is what makes the wave function oscillate. The faster the particle, the more energy, the tighter the wiggles. Inside the barrier, the particle would classically need to have negative motion energy in order to be there, because all its energy and more has been swallowed up by the cost of occupying the forbidden region. In the classical world, negative motion energy is impossible, which is exactly why the classical particle stops and turns back. But the wave function doesn't stop. It does the mathematical thing that corresponds to this strange situation, and that thing is not to oscillate, but to decay. The oscillating wave and the decaying curve are two solutions to the same underlying rule, the equation that governs how wave functions behave, and which one you get depends entirely on whether the particle has enough energy to be where it is. Enough energy, you oscillate. Not enough energy, you decay. The barrier flips the wave function from one mode into the other, from a rolling wave into a fading slope, the instant the particle crosses into territory it can't afford. Now here's the part you must hold on to with both hands, because it's the crux, the thing that makes everything possible. The wave function decays inside the barrier. It does not stop. It does not snap to zero at the boundary. It does not hit the wall and vanish like a ball hitting a brick. It enters the forbidden region with some height, and it slides downward through that region, getting smaller. But getting smaller is not the same as becoming nothing. A slope descending toward a valley floor is still, at every point along the way, above the floor. The wave function shrinks as it penetrates deeper, but at any given depth inside the barrier, it still has some value, some height, some non-zero presence. The particle's wave has leaked into the place the classical particle could never go, and it's fading as it goes, but it has not died. It is, faintly, there. I want to dwell on the precise shape of this decay, because the shape is doing enormous work, and it's more remarkable than it first sounds. The wave function inside the barrier falls off exponentially. Exponential decay is a very particular kind of shrinking, and understanding it is understanding why tunneling happens at all. When something decays exponentially, it doesn't drop by a fixed amount with each step. It drops by a fixed fraction. Imagine the wave function is at some height when it enters the barrier. After a certain distance, it's fallen to, say, 1/10 of that height. The same distance again, and it falls to 100th. Once more, and it's 1,000th. The wave function keeps cutting itself down by the same factor over each equal step of distance. The way a sound fades, the way a hot cup of coffee cools toward room temperature, the way radioactive material dwindles over its half-lives. Each step takes a bite out of what remains, a proportional bite, so the curve plunges steeply at first, and then flattens as it gets closer and closer to zero. And this is the magic of exponential decay, the property that makes the whole phenomenon real. An exponential curve approaches zero, but never actually reaches it. Cut something in half, then in half again, forever, and you get smaller and smaller, but you never get to nothing. There's always a sliver left. A tenth of a tenth of a tenth of a tenth is a tiny number, almost vanishingly small, but it is not zero. It's a real, positive, non-zero quantity, however faint. The wave function, decaying exponentially through the barrier, is shrinking towards zero with every bit of depth it covers, but it never hands over the last of itself, never fully extinguishes, never quite arrives at true nothing. And that refusal to ever fully reach zero is the loophole the universe leaves open. That sliver, that faint surviving thread of the wave function, is the entire reason a particle can be found where it should never be. Because here's what follows, and it follows with a kind of quiet inevitability. The barrier has a width. It is not infinitely thick. It's a hill, and a hill has a far slope, an other side, a place where the forbidden region ends and open space begins again. The wave function enters the barrier at the near edge, decays exponentially as it crosses, getting smaller and smaller, and then it reaches the far edge of the barrier. And at that far edge, because exponential decay never quite reaches zero, the wave function still has some value. Small, yes. Diminished enormously from what it was, but not zero. The wave function emerges from the far side of the barrier with a faint surviving amplitude. And the moment it crosses back out into open space, it starts oscillating again, rolling along as a wave once more, because now the particle is back in a region it can afford, back where motion energy makes sense, back to wiggling instead of decaying. The wave that comes out the far side is much shorter than the wave that went in the near side, much smaller, much fainter. But it's a real wave, travelling away from the barrier, carrying the particle's presence into the space beyond. Stop and look at what we've just built, because this is the answer, fully assembled, and it's worth seeing it whole. The wave function was a tall, rolling wave approaching the barrier. It dropped into a steep exponential slide inside the barrier, and it came out the other side as a small surviving wave, diminished but alive, oscillating away into the open. The particle's wave of probability spans the entire arrangement, tall in front, decaying through the middle, faint but present behind. And we already know what the size of the wave function means at any point. It means the probability of finding the particle there. A non-zero wave function on the far side of the barrier means a non-zero probability of detecting the particle on the far side of the barrier. That's it. That's the whole phenomenon. The particle can be found beyond the wall because its wave of probability extends beyond the wall, faintly but genuinely, and where the wave reaches, the particle can be found. This is what people are pointing at when they say a particle tunnels through a barrier, though I want to flag, even now, that the word tunnel is a little misleading, and we'll return to that. For the moment, sit with the mechanism, because the mechanism is honest and clean and asks you to believe nothing strange except the one strange thing we already established, that the particle is a spread-out wave of probability rather than a tiny ball on a path. Grant that one fact, and everything here is just the wave doing what waves do. It oscillates where it has energy to move, decays where it doesn't, and because the decay is exponential and never fully reaches zero, a thread of it survives across a finite barrier and re-emerges on the other side. No rule was bent. The wave function obeyed its governing equation at every single point, inside the barrier and out. The particle never had to be in a forbidden state, never had to acquire energy it didn't have, never had to do anything other than be the kind of object it actually is. The wall was real. The wave simply doesn't stop at walls the way a ball does. Now let's make this richer by asking the questions that turn a vague picture into a real understanding. Why does it matter how thick the barrier is? Why does it matter how tall? Why does it matter how heavy the particle is? These three things, the width of the barrier, the height of the barrier, and the mass of the particle, control the entire phenomenon. And the wonderful part is that once you understand exponential decay, you can feel in your bones why each one matters without a single equation. Start with width, the thickness of the wall, because it's the most direct. The wave function decays exponentially as it crosses the barrier. The thicker the barrier, the more distance the wave function has to cross, and the more distance it crosses, the more times it gets cut down by that proportional exponential bite. A thin barrier means the wave only survives a short slide before the far edge, so it comes out relatively tall, and the odds of finding the particle on the other side are decent. A thick barrier means a long slide, the wave cut down again and again before it reaches daylight, so it emerges unimaginably faint, and the probability of crossing collapses toward nothing. And because the decay is exponential, this sensitivity is brutal. Double the thickness of the barrier and you don't double the difficulty, you square the smallness, because each unit of width multiplies the shrinkage rather than adding to it. A barrier just a little thicker can be vastly, astronomically harder to cross. This is why tunneling is a phenomenon of the very small. Over the width of an atom, the wave function can emerge with a workable amplitude. Over the width of a grain of sand, that same kind of barrier would crush the amplitude to a number so close to zero that the difference would not matter across the entire age of the universe. Width is merciless, and exponential decay is why. Now height, the tallness of the barrier, meaning how far above the particle's energy the top of the hill sits. The height controls how steeply the wave function decays. A low barrier, one that only just exceeds the particle's energy, lets the wave function decay gently on a shallow slope, so it loses less of itself as it crosses and emerges relatively strong. A tall barrier, one that towers far above the particle's energy, forces the wave function into a steep, plunging decay, dropping fast with every bit of depth, so it arrives at the far edge brutally diminished. The bigger the gap between the particle's energy and the top of the wall, the steeper the slide, the smaller the survivor. Think of it as the difference between wading into a gentle slope and stepping off a cliff. Both descend, but one descends far faster. The taller the barrier rises above what the particle can afford, the faster its wave of presence drains away inside, and the less of it lives to reach the other side. Height steepens the decay, width lengthens it. Together they decide how much of the wave survives the crossing. And then mass, which is the most quietly surprising of the three, because it tells you why tunneling belongs to the lightest things in nature and abandons everything heavy. The mass of the particle controls how readily its wave function penetrates the forbidden region in the first place. Lighter particles have wave functions that decay more gently inside a barrier, so they leak further and survive better. Heavier particles have wave functions that decay far more steeply, plunging towards zero almost immediately upon entering the wall, so they barely penetrate at all before they're spent. A light particle, like an electron, has a wave that reaches surprisingly far into the forbidden region and can emerge from a thin barrier with a real chance of being found. A heavier particle, like a proton, which is nearly 2,000 times more massive, has a wave that dies much faster inside the same barrier, so its odds of crossing are vastly smaller. And a particle heavier still, an entire atom, a molecule, a speck of dust, has a wave function that decays so catastrophically fast inside any ordinary barrier that the surviving amplitude on the far side is, for all practical purposes, exactly zero. Mass is the great suppressor. The heavier you are, the more violently your wave of presence collapses inside a wall, and the more completely the door closes. This single fact is why electrons tunnel constantly and routinely, why protons tunnel rarely and reluctantly, and why you, made of an unfathomable number of heavy particles all at once, will never tunnel through anything at all. We'll come back to that last point, because it deserves its own moment. For now, just hold the pattern. Lighter leaks, heavier dies. Put the three together and you have the complete control panel for tunneling. Thin barriers help, thick barriers devastate. Low barriers help, tall barriers steepen the loss. Light particles slip through, heavy particles are stopped cold. Every one of these effects runs through the exponential decay of the wave function inside the forbidden region, and every one of them is sensitive, often savagely sensitive, because exponentials magnify everything. A modest change in any of these three can swing the probability of crossing by factors of millions, billions, or far, far more. This extreme sensitivity is not a flaw in the picture, it's a feature that nature exploits constantly, and later, it's exactly what lets us build instruments precise enough to feel a single atom, because a phenomenon this sensitive to distance becomes a ruler of exquisite delicacy. But that's ahead of us. Let me return to the wave function itself for a moment, because I've been describing it from the outside, and I want to make sure the inside makes sense too. You might still be carrying a faint version of the marble in the back of your mind, picturing the wave function as a kind of cloud the particle is hiding inside, the particle being a real dot somewhere in that cloud, secretly taking a real path through the wall while we just watch the cloud. I have to be careful to close that door because it's tempting and it's wrong, and it matters for everything that comes next. The wave function is not a cloud concealing a dot. There is no dot threading its way through the barrier. The wave function extending into the forbidden region does not mean the particle is in there somewhere, taking a hidden classical stroll through a place it's not allowed to be. The wave function is the particle's reality, the full description of it, and the fact that the wave function has some value inside the barrier means only this: that the probability of the particle being found inside the barrier, were you somehow to look at exactly the right instant, is small but non-zero. It does not mean the particle is secretly in there. It does not mean the particle passed through every point of the forbidden region, one after another, like a tiny ball rolling across the valley floor it couldn't afford. The wave function is a statement of possibility, not a record of a journey. We'll dig into this much more in what follows, because the difference between possibility and journey is exactly where most of the popular misunderstandings of tunneling come from. But it's worth planting here, in the middle of the mechanism, that nothing about the decaying wave function requires or implies a hidden ball on a hidden path. The wave is the truth. The wave leaks. The leak is a probability. The probability is real. That's all. And it's enough. There's something almost philosophical about this, and I think it's worth feeling rather than just noting. The classical world drew a hard line around the forbidden region and treated it as final. No object may be found here, ever, full stop. The quantum world looks at that same line and reads it completely differently. Inside the barrier, the wave function is small, which means the probability of the particle being there is small, which means deeply unlikely rather than flatly impossible. Beyond the barrier, the wave function is smaller still, yet not nothing, so finding the particle on the far side is rarer still, and yet, faintly, allowed. That shift, from impossible to merely improbable, is the whole transformation, and it is far larger than it sounds. The classical particle lived in a world of certainties, where an outcome either had to happen or simply could not. The quantum particle lives in a world of odds, where every outcome carries a weight, some of those weights heavy, some almost weightless, but vanishingly few of them ever exactly zero. And a weight that's almost nothing is still not the same as no weight at all. That narrow gap between the improbable and the impossible is the entire room in which tunneling lives. The crack of daylight a rolling ball was never given. And this is where the smallness stops being a weakness and becomes, in nature's hands, a near certainty. A single particle facing a real barrier might have a chance of crossing so tiny that you could wait 1,000,000 lifetimes and never see it happen. But nature does not deal in single particles. Inside a single atom, there can be vast numbers of opportunities for a particle to try, attempt after attempt after attempt, an enormous number of throws of the dice every single second. And across a piece of matter you could hold in your hand, the number of particles is so colossal that even an event with a probability of almost nothing becomes something that's happening somewhere within that matter, constantly, ceaselessly, moment to moment. A probability of 1 in a trillion sounds like never, until you realize that trillions upon trillions of attempts are being made all the time, in which case 1 in a trillion becomes a steady drumbeat. The faintness of the surviving wave function makes tunneling rare for any one particle on any one try. The sheer abundance of particles and attempts makes tunneling, in aggregate, common, reliable, and powerful enough to run the engines of stars. We'll see exactly how that pays off, but the seed of it is right here, in the realization that a small probability, multiplied by an unfathomable number of chances, is no longer small at all. So let's gather what we've found, because we've assembled the real machine, and it's worth holding it complete in your mind before we go on. A quantum particle is a spread-out wave of probability, not a ball on a path. When that wave meets an energy barrier it classically cannot cross, it does not stop at the surface. It enters the forbidden region, where it stops oscillating and begins to decay, falling off exponentially as it pushes deeper. Because exponential decay shrinks the wave towards zero without ever fully reaching zero, a faint thread of the wave function survives across a barrier of finite width and emerges on the far side, where it begins to oscillate again as a small but real travelling wave. The size of that surviving wave is the probability of finding the particle beyond the barrier, and that probability, though it can be crushingly tiny, is genuinely greater than zero. How tiny depends, with exponential ferocity, on 3 things: the thickness of the barrier, its height above the particle's energy, and the mass of the particle, with thicker, taller and heavier all driving the odds down, often by colossal factors. And nothing in this entire process violated any law. The wave function obeyed its governing equation at every point. The particle was never in an impossible state. The wave simply doesn't recognize the hard classical edge that a ball would have respected. That truth is going to matter more than ever now, because as honest and clean as this mechanism is, the moment people try to describe it in everyday words, because as honest and clean as this mechanism is, the moment people try to describe it in everyday words, they reach for explanations that sound satisfying, but are flatly wrong. They say the particle borrowed a little energy from the universe and paid it back. They say it teleported. They say it secretly threaded a hidden path through the wall, a real ball on a real trajectory we just couldn't watch. Every one of those stories is false, and every one of them quietly puts the marble back, smuggling the tiny ball on its path right back into a picture that only worked because we threw the ball away. We've built the real mechanism on the wave function, on amplitudes and probabilities, on a wave that decays but doesn't die. To keep that mechanism honest, we now have to go and take apart the comfortable myths, one by one, and see exactly where each of them sneaks the forbidden ball back in, and exactly why the truth, the leaking wave conserving every joule of its energy the whole way through, is stranger, cleaner, and far more beautiful than any of them. We've built the real machine. A particle is a spread-out wave of probability. That wave decays but never quite dies inside a barrier, and a faint surviving thread of it emerges on the far side, where it becomes a real chance of finding the particle somewhere it should never have reached. Clean. Honest. No laws broken. But the moment you try to put that machine into everyday words, something goes wrong. The plain language explanations that get passed around, the ones that feel satisfying, the ones you've probably heard, are mostly false. And they're not false in small, forgivable ways. They're false in a way that quietly smuggles the tiny ball back into the story, the very ball we worked so hard to throw away. So this stretch of our journey is a demolition. We're going to take the 3 most popular explanations of how a particle crosses the wall, hold each one up to the light, and watch it fall apart. And in watching them fail, the true mechanism, the leaking wave, is going to come into even sharper focus, because you understand a thing best when you see clearly what it is not. Let's begin with the most seductive myth of them all, the one that sounds the most scientific, the one that even shows up in otherwise careful explanations. The story goes like this. The particle reaches the barrier without enough energy to cross. So, for a brief instant, it borrows some energy from the universe, just enough to get over the top, and then, Having crossed, it quietly pays the energy back. The universe, the story says, allows this because of the uncertainty principle, which lets energy be fuzzy over short times. The particle takes out a tiny loan, uses it to leap the wall, and settles the debt before anyone notices. It's a wonderful little tale. It has drama, a clever trick, even a real piece of physics name dropped. And it is wrong, thoroughly wrong, and it's worth understanding why, because the error tells you something deep about what's really happening. Here's the first problem. Energy is conserved throughout the entire tunneling process. Not borrowed and repaid, conserved. The particle that comes out the far side of the barrier has exactly the same energy it had when it approached the near side. Measure it before, measure it after, and you find the same value. It did not gain energy crossing the wall. It did not lose energy. It did not pick up a temporary surplus and hand it back. The whole transaction the borrowing story describes simply never takes place. When a particle tunnels, you can check, and the energy ledger balances perfectly at every stage, with no loan, no debt, no fleeting overdraft. The particle on the far side is the same particle with the same energy as the particle that arrived. If energy were really being borrowed and repaid, you'd expect at least the possibility of catching the particle mid-crossing with more energy than it should have, holding its loan. You never do. The books are always balanced. So why does the borrowing story feel right, and where does it go wrong? It goes wrong because it's still secretly thinking of the particle as a tiny ball that needs to physically get over the top of the hill. The whole borrowing idea only makes sense if you believe the particle must, at some point, be up at the peak of the barrier, in the forbidden region, with enough energy to be there. The story invents the loan precisely to pay for that moment, the moment the ball crests the hill. But the ball never crests the hill, because there is no ball, and there is no cresting. That's the entire lesson of the wave function. The particle does not climb to the top of the barrier and go over. Its wave of probability decays through the barrier and emerges thinned on the other side. At no point does the particle need to be sitting at the peak with peak energy, because at no point is the particle a localized object occupying the peak. The borrowing story solves a problem that only exists in the marble picture, and the marble picture is the thing we already discarded. It's an answer to a question the universe never asks. There's a subtler version of this that invokes the uncertainty principle more carefully, and it deserves a careful response, because the uncertainty principle is real and it's tempting to lean on it. The uncertainty principle, in one of its forms, relates energy and time. It says, roughly, that energy and time can't both be pinned down with perfect precision simultaneously. And people take this to mean that over a short enough time, energy genuinely fluctuates, genuinely becomes uncertain, genuinely lets a particle have more energy than it should for a brief window. But this misreads what the uncertainty principle is telling you. The energy-time uncertainty relation is not a license for energy to spontaneously increase and then decrease. It is not a rule that says the universe will lend out energy if the loan is short enough. It's a statement about the relationship between how long a process takes and how sharply its energy can be defined. It describes the spread, the fuzziness, in measured values, the same way the position and momentum version describes the spread in where a particle is and how it's moving. It is a statement about what we can know and how the wave function is shaped, not a mechanism by which conservation laws get suspended for a moment. Energy conservation is not a guideline that bends under time pressure, it holds. The uncertainty principle and energy conservation are both true at once, with no conflict, because the uncertainty principle was never saying energy isn't conserved. It was saying energy and time are bound together in how precisely they can be specified. Those are completely different claims. I want to make this vivid because it's the kind of thing that's easy to nod along to and still get wrong. Imagine you're told that a particle, for a tiny fraction of a second, had a huge burst of extra energy that let it leap the wall and then gave it all back. If that were true, energy conservation, one of the deepest and most thoroughly tested laws in all of physics, a law that has never once been observed to fail anywhere, in any experiment, at any scale, would be getting violated routinely, trillions of times a second, inside every atom. That should make you suspicious immediately. A law that fundamental doesn't quietly break every time a particle tunnels, and it doesn't. The reason tunneling looks like it needs borrowed energy is only that we keep insisting the particle is a ball that has to physically be at the top of the hill. Drop that insistence, return to the wave function, and the need for borrowed energy evaporates entirely. The wave decays through the barrier and emerges with the same energy it always had. There was never a lone, because there was never a moment when the particle needed more than it carried. The forbidden region is forbidden to a ball at a point. It is not forbidden to a wave of probability that's allowed to be small there. So the first myth falls. The particle does not borrow energy from the universe. Energy is conserved at every step, before, during, and after, with no exceptions and no debts. Hold on to that, because it's not a detail, it's central. Tunneling is not a violation of energy conservation dressed up in fancy language. It is energy conservation, fully respected, by an object that happens to be a wave rather than a ball. Now the second myth, which is shorter to state but just as stubborn: teleportation. The idea that the particle vanishes from one side of the barrier and instantly reappears on the other, jumping across the gap in no time at all, skipping the forbidden region by simply not being there for it. This one shows up in casual descriptions all the time. The particle jumps through the wall. It blinks to the other side. It skips over the barrier. And it's wrong in a different way from the borrowing myth, but wrong all the same. There's no jump. Nothing teleports. The wave function is a single connected thing that stretches continuously from the near side of the barrier through it to the far side. It's not two disconnected pieces with a gap between. It's one smooth wave, tall in front, decaying through the middle, faint behind, all continuous, with no break and no instant of disappearance. The particle doesn't cease to exist on one side and pop into existence on the other. Its wave of probability simply extends across the whole arrangement, and where the wave reaches, the particle can be found. Nothing made a discontinuous leap. The amplitude on the far side wasn't beamed there from the near side in zero time. It's the surviving tail of the same continuous wave function that decayed across the barrier. The connection is unbroken the entire way through. And there's a hard physical reason teleportation can't be the right picture, beyond just the shape of the wave function. Nothing in nature travels faster than light, and that includes anything involved in tunneling. The idea of an instantaneous jump, of a particle crossing a gap in zero time, would mean information or matter moving infinitely fast, which the universe flatly does not permit. Tunneling does not let particles outrun light. It does not let them cross space instantaneously. Whatever the detailed timing of a tunneling event, and the timing turns out to be a genuinely subtle question that physicists still discuss carefully, it never amounts to faster than light travel, and it never amounts to a true instantaneous jump. The teleportation picture violates one of the firmest principles we have, the cosmic speed limit, and the real mechanism doesn't need to violate anything. The wave is continuous, the wave extends across the barrier, and the particle is found wherever the wave reaches. No teleportation required, and none permitted. The teleportation myth, like the borrowing myth, is really the marble in disguise. It pictures a ball that has to get from here to there, can't pass through the middle, and so resorts to a magic leap. But the wave function never needed to leap, because the wave function was never confined to a point that had to travel. It was already spread across the whole region. The far side amplitude isn't a ball that arrived by jumping. It's part of a wave that was always there, faintly, across the barrier and beyond. Once you see the particle as the wave, the teleportation story has nothing left to explain, because there's no localized thing making a forbidden journey. There's just a distribution of presence, continuous and connected, thinning across the wall. Which brings us to the third and most subtle myth, the one that's hardest to shake because it's the most reasonable sounding, and it's the one I flagged earlier and promised to return to. The hidden path myth. It goes like this. Sure, the particle is a wave, fine, but when we finally detect it on the far side, it really did get there somehow. It must have taken some route. There must be a true path, a hidden trajectory through the barrier that the particle actually followed, point by point, even if we can't see it. The wave business is just our ignorance of which secret path it took, Underneath it all, surely, there's a little ball that really did slide through the forbidden valley, threading some specific line from one side to the other. This is the marble's last stand, and it's the most important one to defeat, because it's the most convincing. It feels like common sense. The particle was here, then it was there, so it must have travelled along some path connecting the two, even a hidden one. But quantum physics says, carefully and specifically, that this is not how to think about it, and the reasons are subtle and worth laying out. First, the wave function does not describe a particle taking one definite hidden path. It describes a probability of finding the particle in various places. When the particle is detected on the far side, what you've learned is its position at that moment. You have not learned, and cannot extract, a record of where it was at every instant before, a filmed trajectory of its journey through the wall. The measurement gives you a destination, not a route. It tells you where the particle ended up, not the line it traced to get there. And crucially, there is no measurement you can perform that reveals a little ball sliding through every point inside the barrier. If you try to watch the particle inside the forbidden region, to catch it mid-crossing and pin down its location there, you don't find a ball quietly passing through. You disturb the whole situation, you change what's happening, and what you get is not a confirmation of a hidden path, but a different experiment with a different outcome. The clean tunneling you were trying to observe is not the same process once you start watching the interior, because the watching itself is an interaction that reshapes the wave function. The hidden path can't be revealed because it isn't there to reveal. Second, and this is the deep point, asking which exact path the particle took through the barrier is asking a question the quantum state simply does not answer. It's not that the answer is hidden from us by our clumsy instruments, it's that the wave function does not contain a definite path to be hidden in the first place. The particle's reality, as we established at the very beginning, is the wave of probability, not a point on a trajectory. A wave doesn't have a single path. A ripple spreading across a pond isn't taking one route from the centre to the edge, it's spreading everywhere at once. Demanding to know the one true line the particle followed through the wall is demanding that the particle be the marble again, that underneath the wave there's secretly a definite ball doing definite things. And the entire weight of quantum physics, confirmed in experiment after experiment, says no. There is no secret marble. The wave function is not a veil over a hidden trajectory. It is the complete description, and a complete description that contains probabilities rather than a path means there is no path, not merely a path we can't see. I want to be careful and fair here, because this is genuinely contested philosophical territory, and I don't want to overstate. There are serious thinkers who have explored versions of quantum physics in which particles do have definite hidden positions and trajectories, guided by the wave. These are real, mathematically careful ideas, not nonsense. But even in those pictures, the hidden trajectory does not behave like the comfortable classical path the myth imagines. It's not a little ball innocently rolling through the valley with ordinary energy. The trajectory, where such pictures posit one, is shaped by the wave in deeply non-classical ways, and it does not restore the cosy marble intuition that the myth is reaching for. So whether or not you entertain those interpretations, the takeaway is the same. The particle crossing the barrier is not following the kind of ordinary, classical, point-by-point path that the hidden path myth pictures. It is not a tiny ball secretly doing the forbidden thing. The forbidden classical journey, the ball sliding through the valley floor it can't afford, does not happen in any interpretation that matches experiment. Let me sharpen the distinction the myth keeps blurring, because it's the cleanest way to put the whole thing to rest. We must not claim that the particle literally passes through every point inside the barrier in the ordinary classical sense, the way a ball rolling down a road passes through every point of the road in sequence, occupying each one in turn with a definite location and a definite speed. That ordinary, sequential, point-by-point passage is exactly what the forbidden region forbids, and it's exactly what doesn't happen. The wave function having some value inside the barrier does not mean the particle is in there making that classical journey. It means the probability of detecting the particle in there, if you looked at the right instant, is small but non-zero, and detecting it there would itself be a different event from the clean tunneling we're describing. The wave extending into the barrier is a statement about possibility, about where the particle could be found. It is not a description of a ball passing through. Possibility is not journey. The wave being present in the forbidden region is not the same as the particle travelling through the forbidden region as an ordinary object. This distinction is the whole ballgame, and the hidden path myth survives only by ignoring it. Now let me draw one more line, because it's essential and people genuinely confuse the two. Tunneling is not the same thing as a particle gaining enough ordinary energy to go over the top of the barrier. Those are two completely different events. Sometimes a particle really does acquire enough energy, through a collision, through heating, through some kick, to climb over the barrier the honest, classical way, cresting the hill with energy to spare and rolling down the other side. That's not tunneling, that's just a particle with enough energy doing the ordinary thing, the thing the classical world always allowed. Tunneling is the other thing, the strange thing. The particle crossing while genuinely lacking the energy to go over the top, crossing not by climbing, but by the leaking of its wave function through the forbidden region. The signatures are different. A particle that goes over the top needed and used enough energy to be at the peak. A particle that tunnels never had that energy and never was at the peak. It crossed with the same modest energy it carried the whole time, by a mechanism that has nothing to do with cresting the hill. When you see tunneling, you're not watching a particle that found a way to get enough energy. You're watching a particle that crossed without ever getting enough energy, because the wave doesn't need to climb. Confusing the two collapses the entire mystery, because going over the top isn't mysterious at all. The mystery, the real one, the one worth all this care, is crossing without going over. And that is exactly what tunneling is. So let's see clearly what we've cleared away, because the demolition has left the true mechanism standing alone and unobstructed. The particle does not borrow energy from the universe. Energy is conserved at every stage, with no loan and no debt, and the uncertainty principle never said otherwise. The particle does not teleport. The wave function is one continuous, connected thing stretching across the barrier. Nothing jumps, nothing crosses in zero time, and nothing outruns light. The particle does not follow a hidden classical path through the wall. The wave function describes probabilities, not a secret trajectory. Measuring its final position reveals a destination rather than a filmed journey, and the ordinary point-by-point passage of a ball through the forbidden valley simply does not occur. And tunneling is not a particle sneaking enough energy to climb over the top. It is a particle crossing while truly lacking that energy, by the leaking of its wave rather than the climbing of a hill. Notice that every one of these myths failed in the same way, by trying to put the marble back. The borrowing myth needed the ball to be at the peak, so it invented a loan. The teleportation myth needed the ball to cross a gap it couldn't traverse, so it invented a jump. The hidden path myth needed the ball to have taken some route, so it invented a secret trajectory. In each case, the comfortable little sphere on its definite path comes creeping back into the picture, and in each case it has to break something to fit: conservation of energy, the speed of light, or the basic fact that a wave function contains probabilities and not paths. The true mechanism breaks nothing, precisely because it never reintroduces the ball. It keeps the particle as a wave the whole way through, and a wave that decays but doesn't die has no need to borrow, no need to jump, and no need to hide a path. It just has to be the kind of thing a wave already is. There's a quiet beauty in this once it settles. The honest explanation asks you to give up only one thing: the tiny ball, the marble, the point on a trajectory. And in exchange, it hands you a phenomenon that requires no miracles. Every myth tried to keep the ball and pay for it with a miracle, a suspended law, a forbidden leap, a hidden journey. The truth keeps every law intact and pays for it with a single act of imagination, picturing the particle as a spread-out wave of probability rather than a speck. And once you've made that one trade, tunneling stops being a paradox and becomes almost obvious. Of course the wave leaks. Of course a faint thread survives a finite wall. Of course there's a small probability on the other side. Nothing else needed to happen. The wall stayed real, the energy stayed conserved, the speed limit stayed enforced, and still the particle can be found beyond a barrier it could never have climbed. Not because the universe cheated, but because the universe was never playing the game we thought it was playing. It was never moving a ball along a path. It was always shaping a wave of possibility. And a wave of possibility does not stop at walls the way a ball does. We've now done the hard conceptual work. We've built the mechanism on the wave function, and we've defended it against every comfortable distortion. What remains is to watch this quiet, lawful, beautiful phenomenon do its work in the real universe. Because tunneling is not a curiosity confined to chalkboards. The same leaking wave that we've traced so carefully is, at this very moment, holding atoms together and tearing them apart, lighting the stars that fill the night sky, and humming inside the machine you're using to hear these words. The mechanism we've assembled, energy conserved, no teleportation, no hidden path, just a wave that decays but refuses to fully die, is about to explain why certain atoms crumble after billions of years, why the sun shines at all when by rights it shouldn't be hot enough, and how we learn to feel the shape of a single atom with our instruments. The abstract wave is about to become the most concrete thing in the world. So far, this has all lived in the abstract. A wave, a barrier, a faint surviving thread of probability. It's elegant, but you might reasonably ask whether any of it matters outside a physicist's imagination. The answer is that it matters more than almost anything else in the physical world, because the leaking wave we've spent all this time understanding is, right now, doing three enormous jobs at once. It's making certain atoms fall apart after sitting quietly for billions of years. It's lighting every star in the sky, including the one our planet orbits. And it's sitting inside the device you're using to hear these words, doing work we've learned to put to use on purpose. The wave is not a chalkboard curiosity. The wave runs the universe. Let me show you how, starting deep inside the atom, in the smallest and most tightly sealed prison nature ever built. At the center of every atom sits the nucleus, a dense knot of particles holding almost all the atom's mass in a space staggeringly smaller than the atom itself. Inside that nucleus, particles are bound by the strong nuclear force, so powerful at close range that it overwhelms everything else, gluing the nucleus into a tight, stable bundle. But the strong force has a peculiar character. It's ferociously strong, but only over an incredibly short distance. Get the particles close together and it clamps down with overwhelming grip. Pull them even slightly apart, beyond its tiny reach, and it falls off almost instantly, becoming negligible. Meanwhile, there's another force at work inside the nucleus, the electrical repulsion between the positively charged pieces, which, unlike the strong force, reaches out across longer distances. So a particle inside the nucleus finds itself in a remarkable situation. Close in, the strong force holds it captive in a deep well, an energy valley it's trapped at the bottom of. But surrounding that valley, like the rim of a volcano, is a wall, an energy barrier formed where the electrical repulsion dominates, a hill the particle would have to climb to escape. This is the setup for one of the most important examples of tunneling in all of nature, alpha decay. In certain heavy, unstable atoms, particles cluster inside the nucleus into a tight little bundle of 2 protons and 2 neutrons, a unit so stable on its own that it has its own name, the alpha particle. This alpha particle sits inside the nucleus, trapped in that deep energy valley, surrounded by the barrier of electrical repulsion. And here is the crucial fact, the one that connects everything. The alpha particle does not have enough energy to climb over that barrier. By the strict accounting of classical physics, it is sealed in. The wall around it is taller than the energy it carries. It should be imprisoned forever. The nucleus should be permanently, eternally stable, because the alpha particle can never crest the wall that holds it. And yet these atoms decay. Given enough time, the alpha particle escapes. It leaves the nucleus entirely, flies away, and the atom transforms into a different element. This is alpha radiation, the radiation given off by elements like uranium and radium and many others, discovered well over a century ago and studied ever since. The alpha particle gets out of a prison it could never climb out of. And for a while, this was a genuine mystery, because by every classical rule, escape was impossible. The wall was too high. The particle was sealed in. How does it get out? You already know the answer, because we built it together. The alpha particle is not a tiny ball trapped at the bottom of a valley. It's a wave of probability. And that wave does not stop dead at the wall of the nucleus. It extends into the barrier, decays exponentially as it crosses, and emerges on the far side with a faint but non-zero amplitude. The alpha particle's wavefunction leaks through the barrier of electrical repulsion exactly the way every tunneling wave leaks through every barrier. There's a small probability, on any given attempt, that the particle will be found outside the nucleus rather than inside it. And the moment it's found outside, it's free, repelled away by the very electrical force that used to be its wall, flung off into the world as alpha radiation. The particle never climbed the barrier. It never gained the energy to crest the wall. Energy was conserved the entire time. Its wave simply leaked through the forbidden region, and the leak, repeated over countless attempts, eventually carried it out. Now here is where it becomes genuinely beautiful, where the abstract sensitivity we discussed earlier turns into something you can see in the world. Remember that tunneling depends, with exponential ferocity, on the height and width of the barrier and the energy of the particle. A small change in any of those swings the probability of crossing by enormous factors. Inside different heavy atoms, the alpha particle faces slightly different barriers and carries slightly different energies. And because tunneling is so savagely sensitive to those small differences, the rate at which different elements decay varies across a range so vast it almost defies belief. Some unstable atoms decay in fractions of a second, others take billions of years, longer than the current age of the Earth, longer than the age of the solar system. The very same mechanism, the leaking wave, produces half-lives spanning an unimaginable range, from the blink of an eye to timescales that dwarf the history of our planet. And the reason that range is so staggeringly wide is precisely the exponential sensitivity we identified. A modest difference in the barrier or the particle's energy gets magnified by the exponential into a difference of factors of trillions upon trillions in how long the atom survives. The wild spread of radioactive half-lives, one of the most striking facts in all of nuclear physics, is exponential tunneling sensitivity written across the elements. Nothing else explains why one atom falls apart in an instant and its near cousin sits stable for eons. The wall is a little taller, a little wider, the wave decays a little more steeply, and a fraction of a second becomes a billion years. Sit with that for a moment, because it reframes radioactivity completely. The reason a lump of uranium is dangerous, the reason certain rocks tick on a Geiger counter, the reason we can date ancient stone and bone by counting decays, all of it traces back to a wave leaking through a wall it could never climb. The atom is not a stable little machine that occasionally malfunctions. It's a wave particle sitting in a leaky prison, and the leak, exquisitely tuned by the exponential, sets the clock. Every alpha decay is a tiny act of tunneling, a wave function slipping through a barrier, energy conserved, no path taken, no energy borrowed, just the quiet refusal of a wave to stop where a ball would have stopped. Now lift your eyes from the atom to the sky, because the same mechanism that lets particles out of nuclei is, on a vastly larger stage, letting particles into them, and in doing so, it lights the stars. Look up at the sun. It pours out heat and light every second, has done so for billions of years, and will do so for billions more. All that energy comes from nuclear fusion in the core, where the nuclei of light elements are forced together to make heavier ones, releasing energy in the process. The sun shines because hydrogen nuclei fuse into helium deep in its heart. But there's a problem with this story, a problem so severe that for a time it looked like the sun shouldn't be able to shine at all. The problem is the same wall we just met, the electrical repulsion between positive charges, except now it's working against fusion instead of against escape. To fuse, two nuclei have to get extremely close enough for the strong force to grab them and bind them together. but both nuclei are positively charged, and like charges repel. As they approach, the electrical repulsion between them rises and rises, building a steep barrier, a hill that gets taller the closer they get. To fuse, they have to climb over that hill of repulsion, get close enough for the strong force to take over and snap together. And here is the crushing difficulty. At the temperatures found in the core of the Sun, hot as it is, the nuclei are not moving fast enough to climb over that barrier. They don't have enough energy. By the strict classical accounting, the nuclei approach each other, feel the repulsion build, slow down, stop short of contact, and bounce apart, never touching, never fusing. The hill of repulsion is too tall for the energy they carry. The Sun, by classical physics, is not hot enough for its own nuclei to fuse. The star should be dark. But the Sun shines anyway. Something is carrying those nuclei across a barrier their energy can't classically surmount. And by now you can say what it is before I do. The nuclei are waves of probability, not tiny balls, and their wave functions do not stop at the wall of repulsion. As two nuclei approach and the barrier between them rises, their wave functions leak into that barrier, decay across it, and retain a faint amplitude on the far side, the side where they're close enough for the strong force to bind them. There's a small probability, on any given near collision, that the nuclei will be found close enough to fuse, even though they never had the energy to climb all the way over the repulsion. They tunnel through part of the electrical barrier. The wave crosses what the ball could not. And fusion happens, not because the nuclei found enough energy to crest the hill, but because their waves leaked through it. I want to be precise about what's happening here, because it's a slightly different flavour of tunneling than the alpha decay case, and the difference matters. In alpha decay, the wave leaked outward, letting a trapped particle escape. In fusion, the waves leak through a barrier between two approaching particles, letting them reach each other when they couldn't otherwise. The nuclei don't have to climb the entire wall of repulsion. They climb part way, using the modest energy their motion gives them, and then tunnel through the remaining stretch of the barrier that their energy alone could never cover. The thermal motion in the star's core gets them partway up the hill. Tunneling carries them the rest. And because, once again, tunneling is exponentially sensitive to the height and width of what's left to cross, the rate of fusion depends ferociously on temperature and on the energies of the nuclei. This sensitivity is part of why stars burn at the steady, regulated pace they do, slowly enough to last billions of years rather than detonating all at once. Now feel the weight of this, because it's one of the most profound facts in all of science. Without tunneling, the Sun would not shine. The core is not hot enough, the nuclei not energetic enough to fuse by climbing the barrier the classical way. Every photon of sunlight that has ever warmed your face, every ray that grew the plants that feed every living thing, every bit of light that has driven the climate and the weather and the entire web of life on Earth, all of it exists because waves of probability leak through walls of electrical repulsion in the heart of the Sun. The same quiet phenomenon that lets an alpha particle escape a nucleus lets two nuclei find each other against the force that should keep them apart. Tunneling does not merely happen in stars. Tunneling is why stars work at all. The night sky, every point of light in it, is lit by this mechanism, repeated in unimaginable numbers in the cores of countless suns across the universe. The wave we traced so carefully through a chalkboard barrier is, at this scale, the reason the cosmos is full of light instead of cold and dark. And this is where the faintness of a single tunneling event stops being a limitation and becomes, instead, the engine of a star. The core holds a number of nuclei beyond any imagining, and they approach one another an astronomical number of times every second. Multiply a probability that is almost nothing by a number of attempts that vast, happening ceaselessly in every cubic centimetre of the core, and the trickle of successful crossings becomes a flood. No single pair of nuclei is likely to fuse on any given approach, but so many approaches occur, so relentlessly, that fusion proceeds as a steady, regulated blaze, pouring out energy second after second for billions of years. The star does not rely on luck. It relies on sheer number, on giving an event that almost never happens so many chances to happen that it becomes the most dependable thing in the sky. This is exactly the payoff we anticipated. Rare for one particle, certain in aggregate. And the aggregate is a star. And the stars do more than shine, they build. Once the simplest fusion is underway, the same tunneling that fuses hydrogen into helium keeps reaching further, coaxing helium nuclei together, then heavier products still, each step a matter of waves leaking through walls of ever steeper repulsion, because the more positive charge a nucleus carries, the higher the barrier any newcomer must cross to join it. This is how the heavier elements are forged. The carbon that forms the backbone of every living molecule, the oxygen you're breathing, the nitrogen in every strand of your genetic code, the calcium in your bones, the iron in your blood. All of it was assembled inside stars, nucleus by nucleus, through fusion reactions that depend on tunneling to happen at all. Without the leaking wave, the universe would be stuck with its lightest ingredients, a thin broth of hydrogen and helium, and almost nothing else. No carbon, no oxygen, no rock, no planets, no chemistry rich enough for life. The same quiet phenomenon that lets two nuclei find each other against the force that should keep them apart is, step by step, the reason there is anything interesting in the universe to be made of. You are not only warmed by tunneling, you are built from its products. Every atom in your body heavier than helium was manufactured by waves, crossing barriers they could never have climbed, in the cores of stars that lived and died before our sun was born. The same mechanism even governs how some of the heaviest atoms tear themselves apart. The largest, most overloaded nuclei can undergo spontaneous fission, deforming, stretching, and pinching until they are poised to break in two, but held back by a barrier their own energy cannot overcome. Whether such a nucleus splits depends, once again, on whether its wavefunction can leak through that barrier of deformation, tunneling it across the threshold from whole to broken. The line between a heavy nucleus that holds together for ages and one that suddenly flies apart is, in these cases, drawn by the same leaking wave we have followed the whole way through. Creation and destruction, the forging of elements and the splitting of atoms, both turn on a single, quiet act, a wave function reaching through a wall that should have contained it. We did not merely discover tunneling, we learned to engineer with it, to lean on its strange reliability, to make the refusal of a wave to stop at a wall into a foundation we can build instruments and computers upon. Let me bring this all the way down now, from the heart of the sun to something you could hold in your hand. Because tunneling is not only a thing that happens in nuclei and stars, where we can only watch from afar. We have learned to use it, deliberately, in machines we build on purpose. And the most beautiful example is an instrument that lets us do something that sounds impossible. See individual atoms. It's called the scanning tunneling microscope. The principle behind it flows directly from everything we've established, especially the exponential sensitivity to distance. Imagine an incredibly sharp metal tip, sharpened down so finely that it ends in essentially a single atom, brought extremely close to a surface you want to examine. Close but not touching, separated by a tiny gap. That gap is a barrier. The electrons in the tip would have to cross empty space to reach the surface, and empty space, to an electron at these energies, is a forbidden region, a wall it classically cannot cross. But electrons are light, the lightest charged particles that matter here, and we know that lighter particles tunnel most readily. So the electrons tunnel across the gap. Their wave functions leak through the empty space between tip and surface, and a tiny current flows, a tunneling current, carried by electrons crossing a barrier they could never classically cross. Here's the part that turns this into a microscope of almost magical precision. That tunneling current depends exponentially on the width of the gap, because the gap is the barrier, and tunneling is exponentially sensitive to barrier width. Move the tip a tiny bit closer to the surface, and the current surges. Move it a tiny bit farther, and the current plummets. The exponential makes the current respond enormously to changes in distance so small they're a fraction of the size of an atom. So as you drag the tip across the surface, keeping track of how the tunneling current rises and falls, you are effectively feeling the bumps and dips of the surface at the scale of individual atoms. Where an atom bulges up, the gap narrows, the current surges, and you know something is there. Where there's a valley between atoms, the gap widens, the current drops. By scanning the tip back and forth and reading the current, you build up a map of the surface so fine that individual atoms appear as distinct bumps, laid out in their actual arrangement. We can see atoms. We can watch them in their lattices, even nudge them one at a time. And the entire instrument works because electrons tunnel through a gap they classically cannot cross, with a current so exquisitely sensitive to distance, thanks to the exponential, that it resolves individual atoms. The very sensitivity that gives radioactive half-lives their wild range is the sensitivity that lets this instrument feel a single atom. The same exponential, harnessed two completely different ways. And it doesn't stop there. Tunneling is woven through the technology that runs your life, often quietly, sometimes as a tool, and sometimes as a nuisance. There are electronic components called tunnel diodes, deliberately designed so that electrons tunnel through a thin barrier inside them, giving the device unusual and useful electrical behavior that engineers exploit in certain high-speed and specialized circuits. The tunneling isn't an accident in these, it's the whole point, the operating principle, electrons crossing a designed barrier to make the component do its job. And in the broader world of modern electronics, in the chips that fill our computers and phones, tunneling shows up on both sides of the ledger. In some memory devices, electrons are deliberately tunneled through thin insulating barriers to store information, the tunneling current carefully controlled to write and erase data. But as engineers have pushed to make the components on chips smaller and smaller, packing more of them into less space, the insulating barriers that are supposed to keep electrons where they belong have grown so thin that electrons begin to tunnel through them when they shouldn't. This unwanted tunneling, electrons leaking across barriers that were meant to contain them, becomes a real problem, a source of wasted power, and a fundamental obstacle to making components ever tinier. The same phenomenon that we use on purpose in one place haunts us in another, an unavoidable consequence of building things so small that the wave nature of the electron can no longer be ignored. When you hear that there are limits to how small computer chips can get, that we're running up against the physics of the very small, tunneling is a large part of what that means. The leaking wave, helpful in one design, becomes the wall we keep running into as we try to shrink the machine. Let me add one more human-built example, because it's among the most precise and important tools we have, and it shows tunneling taken to a refinement that borders on the miraculous. When two superconductors, materials that carry electrical current with no resistance at all, are placed close together with a paper-thin barrier between them, something remarkable happens. Pairs of electrons tunnel across that barrier, leaking through the insulating gap exactly as our mechanism demands, and the result is a junction whose electrical behavior is so exquisitely regular, so tightly governed by fundamental constants of nature, that we use it to define our standards of voltage with extraordinary accuracy. The behavior of this tunneling junction is so reliable and so deeply tied to the basic constants of physics that it has become a bedrock of precision measurement, a place where the strange leaking of waves through walls is harnessed to anchor the units we measure the world by. And these same tunneling junctions sit at the heart of many of the devices being built to make quantum computers, where their delicate, controllable behavior is used to store and manipulate quantum information. The leaking wave, which began for us as an abstraction on a chalkboard, has become a component, manufactured deliberately, relied upon, a working part of some of the most advanced machines humanity has ever attempted to build. So the same mechanism, from one end of the scale to the other, ties the whole physical world together. It empties nuclei and dates ancient rocks. It fills nuclei, lights the stars, and forges the very elements your body is built from. It lets us read the surface of the world one atom at a time, store our data, anchor the units by which we measure electricity, and reach toward machines that compute by quantum rules, while at the very same time setting a fundamental limit on how small our ordinary machines can ever grow. helpful in one place and obstructive in another, ancient in the cores of stars and brand new in our laboratories, the same quiet phenomenon runs through every one of them. The smallest, strangest behaviour in nature turns out to be one of the busiest, holding our world together and lighting the sky above it all at once. But I owe you a return to a promise I made much earlier, because it's the question that protects all of this from sliding into nonsense. If particles tunnel through walls all the time, why don't you? Why can't a person walk through a closed door? Why doesn't a ball you throw at a wall occasionally just appear on the other side? If barriers aren't absolute, if walls can be crossed, why are the walls of your house so reliably solid? The answer brings us all the way back to the control panel we built, and it's one of the most important things to understand about tunneling, because it's exactly what keeps the everyday world sane. Remember the three controls: the width of the barrier, its height, and the mass of the particle, all running through the exponential. And remember that mass is the great suppressor. The heavier the particle, the more violently its wave function collapses inside a barrier, the faster the decay, the smaller the surviving amplitude. Electrons tunnel readily because they're extraordinarily light. Protons tunnel far less readily because they're nearly 2,000 times more massive. And you, a human being, are made of an almost incomprehensible number of particles, every one of them heavy on this scale, all of which would have to tunnel together, in coordination, across a barrier vastly thicker than any atom, a barrier as wide as a wall. Run that through the exponential, and the probability doesn't just become small, it becomes a number so unimaginably close to zero that calling it impossible is, for every practical purpose, entirely fair. The mass is enormous, the barrier is enormous in width, and the exponential takes those enormous numbers and produces a probability so vanishingly tiny that you could wait not just for the age of the universe, but for that span repeated more times than there are atoms in the cosmos, and never once expect to see a person tunnel through a wall. The phenomenon is real. The probability is genuinely greater than zero. But greater than zero and meaningfully possible are not the same thing when the exponential has finished crushing the number. For anything bigger than the smallest, lightest particles, crossing anything wider than the smallest barriers, tunneling switches off so completely that the world becomes solid and dependable. Walls become walls again, and the strange permeability of the quantum realm vanishes beneath the weight of ordinary mass and ordinary distance. This is why tunneling is common and crucial at the quantum scale, and effectively invisible for ordinary objects. It's not that big things obey different laws, it's that the same law, the same exponential, produces a workable probability for a light electron crossing a gap a fraction of a nanometer wide, and produces an utterly negligible probability for a heavy object crossing a barrier you could lean against. The transition is not a change in the rules, it's the exponential doing what exponentials do, magnifying the difference between small and large until small becomes routine and large becomes never. The quantum world tunnels constantly. The everyday world doesn't, not because the everyday world is exempt, but because the everyday world is made of things too heavy and barriers too wide for the wave to survive the crossing. The door is solid for exactly the same reason the sun shines, the mathematics of the leaking wave. In one case, the leak is generous. In the other, it is so suppressed that it might as well not exist. And so we arrive back where we started, at the wall and the particle that could not climb it. But we arrive understanding what we did not understand before. We asked at the very beginning how a quantum particle can cross a barrier that should stop it. And the answer, fully assembled, is that the classical idea of a particle, the tiny ball following one definite path, is incomplete. It was never the whole truth, only a beautifully reliable approximation that works for marbles and planets and everything large, and quietly fails for the smallest things. A quantum particle is not a ball on a path. It is a wave of probability, a quantum state spread across space, and a quantum state does not stop abruptly at a classically forbidden barrier. Its wave function penetrates the wall, decreases exponentially through it, and can retain a faint non-zero amplitude on the far side, so that the particle can be found there with a real, calculable probability, while energy is conserved at every single step, with nothing borrowed, nothing teleported, and no hidden classical path threaded through the forbidden region. The barrier was never an absolute wall. That was the illusion we carried in from the world of large things. In the quantum world, a barrier does not deliver a verdict of yes or no, cross or reflect. It sets a probability. It suppresses the wave, often by staggering factors, sometimes by factors so enormous that the suppression amounts, for all practical purposes, to a perfect seal. But suppression is not annihilation, and the exponential that crushes the wave so brutally still, always, leaves a sliver behind. It drives the probability down towards zero without ever quite reaching it, across any barrier of finite width. And that refusal of the wave to ever fully vanish, that thin surviving thread of amplitude on the far side of a wall that should have been impassable, is the whole reason quantum particles cross barriers that should stop them. The classical wall says never. The quantum wall says almost never. And almost never, repeated across the unfathomable abundance of particles and attempts that fill every atom and every star, becomes the radioactivity that ticks in ancient stone, the fusion that burns in the heart of every star, and the current that lets us read the surface of the world one atom at a time. The wall is real. The energy the particle lacks is real. But the wave does not stop where a ball would stop. And in that quiet, lawful, beautiful difference lies the answer to how anything at all gets across a barrier that should have held it forever.